Okay, so next we will talk more about delta S for a closed system. The first concept we will introduce here is called isentropic process. Isentropic is very useful. So first of all, what is the criteria you call a process isentropic? If you can satisfy those two requirements, then you can call the process isentropic. The first requirement is this process has to be adiabatic. Adiabatic means there's no heat transfer, Q equal to 0. And then second requirement is reversible. Reversible, which means entropy production, sigma, is equal to 0. You can refer to what we learned under Clausius inequality. If sigma is greater than 0, that means the process is irreversible. If sigma is equal to 0, that means this process is reversible. And if sigma is less than 0, that means the system is impossible. Your design is wrong because it violates second law. Okay, so if you can satisfy those two requirements, then you can call the process isentropic. And why do we like isentropic so much? If the process is isentropic, you can say the change of entropy must be 0. Or in other words, the entropy is constant for this process. Okay, so that's the first important concept we learned, isentropic process. It's very useful because it gives us a constant entropy. Okay, and then the next thing we recall is we learned the definition of entropy is derivative capital S equal to delta Q over T if the process is reversible. This is the definition of entropy, capital S. And now we can rewrite this equation. We can move temperature to the left-hand side. So it becomes T times ds. Right-hand side is delta Q. Okay, so now we can discuss two cases. The first case is if your delta Q is positive, which means the system gains heat. What's going to happen to this equation? If delta Q is positive, so left-hand side must be positive. And temperature is always positive, so derivative capital S must be positive, which means entropy goes up. So now if we translate that, what does it mean? If the system gains heat, what's going to happen is system will gain entropy because entropy goes up. Derivative entropy is positive. That means entropy goes up. When delta Q is less than 0, which means the system loses heat, then left-hand side T times ds will also be negative, but temperature is always positive, so derivative S this time must be negative. And how do we translate that? If the system loses heat, what's going to happen is derivative S will be less than 0, which means entropy will become smaller. So the system also loses entropy. Okay, so this concept is very handy later on. What you need to remember is if your system gains heat, your system also gains entropy. If your system loses heat, your system also loses entropy. Okay, so that's the second one. And then the third one we need to cover today is the area representation. Okay, so before we learn something new, let's recall what we learned before. What we learned before is if you have a P versus V diagram like this from 1 to 2, which is an expansion process. And we learned from before the area under the curve tells you one thing. And what is that? Work. Integral P dV V1 to V2 is equal to area under the curve. And then we move down to P versus nu diagram. P versus nu diagram. Same expansion process, but on a different diagram. This time is P versus nu. And the area under the curve tells us something very similar. And what is that? Let's recall nu is equal to volume over mass. So keep that in mind. Everything will be divided by mass. And what we learned from before is area under the curve 1 to 2 is equal to work, this time divided by mass. This is what we learned from before. On P versus V diagram, the area represents work. On a P versus nu diagram, the area represents work per unit mass. Okay, so this is something we learned before, and now we introduce something new. Because in the beginning we said we will no longer use T versus nu diagram, but we will change to T versus capital S diagram. And what is the reason for that? For example, if you have a process like this, 1 to 2, where you gain heat, you also gain entropy, what does the area under the curve represent? First of all, if you have a T versus nu diagram, the area under the curve doesn't represent anything. That's the reason why we do not prefer T versus nu diagram anymore. The reason why we prefer T versus S diagram is because the area under the curve on a T versus S diagram actually tells us something. So what does it tell us? Let's recall from the beginning of this week's video. Q is equal to integral T times D, capital S. This comes from the definition of entropy. So now let's take a look. T on this diagram is the y coordinate, which is the height, multiplied by entropy capital S, which is the x coordinate or the length for this diagram. Height multiplied by length, what does that give you? That gives you the area. So now we realize if you have a T versus S diagram, capital S, the area under the curve actually tells you heat transfer. Just like before, if you have a P versus V diagram, the area under the curve tells you work. And this time it is heat transfer Q. And now, same as before, we do not usually use capital S but lowercase s. So really we usually use the diagram T, temperature, versus lowercase s. And then you have the same process 1 to 2. And then you have a curve. You have the area under the curve. What does the area under the curve mean this time? Area under 1 to 2 this time tells you, remember, lowercase s is equal to capital S over m, which means you just need to divide everything by mass. So this time area under 1 to 2 is heat transfer divided by mass. Okay, so that's why we usually prefer T versus lowercase s diagram, because the area under the curve tells us heat transfer per unit mass, Q over m. So now we can visualize how much heat transfer that we have.